Welcome to Chapter 20 of our course MEC410. This week we're going to study machine frames and bolted connections and welded joints. The homework consists of some description and images on the next 5 slides, so I'm not going to go over it here. The slides are stored in the assignments folder and are fairly self-explanatory. This slide shows some welded frames for production equipment. On the left, you see a square box frame with welds at the corners, which creates an incredibly strong structure. And on the right, you have a square box frame with welds at corners, but some of the frame is open, and you have different heights for different elements of the frame. And that's fairly typical of these square frames, that they will be dimensioned around the size of the components that are stored in them to make production equipment. Sometimes you have enormous welded frames. This one's got to be at least 20 feet high. Looks like it could be a gantry for building boats or building trucks. You can go to the website and read more about this company. Maybe they'll explain it. And when you go to the gym, you do see welded frames for gym equipment. I photographed this one at my gym. They thought I was a little weird, taking pictures of a blank frame. Usually you see enormous bulked up guys taking pictures of themselves doing weightlifting. And welding is standard in all automobile frames, and it's the first step in the automobile assembly process. If you click in the lower right corner, you'll have a link to a video on automated assembly of Mercedes-Benz cars at their factory in Georgia. And welded frames are used for hauling equipment. This one is a welded U-shaped beam that forms the trailer for hauling boats. There are many issues to consider when designing a welded joint. First, you have to estimate the forces exerted by the components of the machine through mounting points such as bearings, pivots, brackets, feet of machine elements. And you have to define the manner of support of the frame itself. You might consider some combination of welding and bolting. And you have to determine what the precision of the system is. Welding does not give you well-defined locations, and if you need exact locations of equipment and exact allowable deflections of components, this may not be the way to go. You want to understand the environment in which the unit will operate and the quantity of production units that you need to make. If you're only making one frame, you'll probably just use hand welding equipment, but if you're going to make dozens or hundreds, you might consider automated welding equipment the way the automobile companies do. And you should understand if you've got any analytical tools such as computerized stress analysis to help you understand just how large you need to make the frame and how strong you need to make the welds. There are some optimal shapes of frames that people figured out a very long time ago. Typically it's forming welded frames or riveted frames and building them in terms of a truss. This bridge opened in 1931. For those of you who live in the New York City area and who love traffic and sitting in traffic jams, you know it as the busiest bridge in the world, where one accident on the bridge causes 60 to 90 minute traffic backups, and I've certainly had my share of them over the years. There's 100 million cars crossing this bridge annually, and everyone pays the highest toll in the world, which increases annually. It uses double diagonal bracing for the main supports and single diagonal bracing to hold up the lower roadway. The lower roadway was built as an addition in the mid-1950s to double the throughput of traffic. If you click on the link down below, you'll be able to read what bridge it is, but spoiler alert, it's called the George Washington Bridge. It connects northern Manhattan in New York City with New Jersey and spans the Hudson River. Houses are made of wood frames covered with wood planks, even extremely expensive one. And the frames for both the roof and walls use a conventional cross bracing. You can see these photos up on the roof, and you see these angled beams that make up part of the roof. And this construction is fairly standard. Usually they're screwed together in some type of standard pattern that can be mass produced as the house is built. TIG welding, otherwise known as TIG welding, short for tungsten inert gas welding, uses a non-consumable tungsten electrode to create the weld joint. A filler metal is the raw material for the joint, and that filler metal comes from this filler rod that is held or fixtured right at the weld location when the torch is lit. So here's your filler rod, there's the weld going around in a circle for these circular tubes. And the weld area is shielded from atmospheric contamination with an inert gas such as helium or argon. Current is conducted across the arc via plasma, plasma being a mix of ionized gas and metal vapor. TIG welding is commonly used to weld stainless steel or aluminum tubes. It's a slow process, but it does yield a very high quality welds. And it's also used in bicycle frames. You know that there is a weld at different locations of the frame. When you inspect where the frame elements meet, if you can feel along with your fingers and feel these little ridges and bumps, which look like this before they're painted, that's your clue that there is a TIG weld at that location. MIG welding, known as MIG welding for short, stands for metal inert gas welding. In this type of welding, we create an electric arc between a consumable wire electrode and the workplace metal. This heats the workplace metal, causing them to melt and join. It is mostly used for large ferrous steel frames due to the fast speed of the process compared to TIG welding. A shielding gas, which consists of a 75% argon, 25% carbon dioxide, or 90% argon and 10% carbon dioxide, shields the process from contaminants in the air. Usually use DC voltage with greater than a 50 amp current from a large power source. MIG welding can be done in portable fashion. Here is a welder manually MIG welding this enormous carbon steel pipe. The various types of weld joints are associated with the geometry of the weld. In a fillet weld, the weld is a triangular shape that joins a vertical and a horizontal member. The width and the height of the triangle is equal to W, and T, the critical dimension along this hypotenuse, is equal to 0.707 times a W. A square butt weld gets its name from the fact that the edges of the two pieces of metal are parallel to each other, forming the sides of a square. A single bevel gets its name from the fact that one edge of one of the pieces of metal is angled, hence bevel-shaped. Double bevel has two edges that are angled, hence double beveled. Single V says that the edges of the two pieces of metal form a V shape. Double V, you have two pair of angled edges, quadruple bevel if you will. A U-groove butt joint has a U-shape cut out in the two pieces of metal, and you can also do a U-groove with a corner joint. Four different types of loading are considered when designing a weld joint. You have a direct tension and compression, direct vertical shear, bending, and twisting. These are the same loadings that you have on beams. The method allows you to perform calculations very similar to that used for the beams. And in general, the weld is analyzed separately for each type of loading to determine the force per inch of weld size due to each load. The loads are then combined vectorially, similar again to beams, to determine the maximum force. The maximum allowable force per inch of weld size, small f, is compared with the allowable force per inch in table 20-3 for various different types of electrodes and materials used. You have geometric terms which are used to calculate the force per inch. You have A sub W, which is somewhat analogous to an area. S sub W is roughly analogous, but not dimensionally, to a moment of inertia, and J sub W is roughly analogous to a polar moment of inertia. But the units of measure are different because you're attempting to calculate a force per inch of leg. So that the force per inch of weld size for direct tension of compression is the tensile or compressive force divided by A sub W. For vertical shear, small f equals the vertical shear force divided by A sub W. In bending of a weld joint, the force per inch, small f, is the moment divided by a geometry factor S sub W. And for twisting or torsion, the small f is equal to the torque times distance between max force location and the centroid of your weld pattern, divided by J sub W, which is your geometry factor for twisting. Here's how we calculate some of the weld geometry factors in figure 20-8. If your weld is one line for two perpendicular structures, then you calculate A sub W as just the length of the line. S sub W is the height of the horizontal member squared divided by 6, where the moment M is the load P times the moment arm A. And in torsion, when you have two structural elements parallel to each other, you put a weld line on one end, and J sub W, the geometry factor for that condition, is the length of that weld line cubed divided by 12. C is the distance from one edge of the weld to the centroid of the weld, and that is just half the height D. If you have two lines of welding, you have D is the height of the lines and B is the distance between the lines. Here is a square beam that is welded to a perpendicular metal slab, and you have one weld line on one side, one weld line on the other side. A sub W is then twice the height D. S sub W then is the height of the line, D squared divided by 3. And J sub W takes into account both the height D and the cross-sectional width of the square beam, and it's equal to D times 3B squared plus D squared divided by 6. In the general procedure for designing welded joints, we first define what the geometry of the joint is, and we use figure 20-8 and pick the best solution out of that figure. And we identify the types of stresses to which the joint is subjected. Could be bending, twisting, vertical shear, or direct tension or compression. We determine the magnitude and the direction of the force on the weld, combine the forces vectorially at the point or points where the forces appear to be maximum on the weld joint, and then we divide the maximum force on the weld per inch by the allowable force from table 20-3 to determine the required leg size for the weld. And note that when thick plates are welded, there are minimum acceptable sizes for the length of the weld. The plate thickness in this picture here is this height, or it's the width of the vertical member. And for any plate thickness, if you calculate a minimum leg size for a weld below what table 20-4 recommends, you round up to the sizes as shown in the table. Here's example 20-2, where we are designing a welded joint with a plate for a bracket. In this problem, we're designing a bracket similar to that of figure 20-4, which I've repeated for you on this slide. But instead of using 4 bolts as that figure in our textbook does to attach the bracket to the upright column, we're going to use welding to attach the bracket in the column. And we're going to have a weld structure in the form of a C. These red lines denote the welding lines. The bracket is 6 inches high, shown as dimension D. It's made from ASTM 836 steel, having a thickness of a 1/2 inch, so the distance into the page of this bracket is a 1/2 inch. The column, here's our column, is made of A36 steel also. It's 8 inches wide. That's the distance from the left edge to the right edge of the column. And the welded bracket is such that the edge of the bracket to where the bracket ends is 4 inches. Shown here where my mouse is the centroid of the weld pattern, and that comes from using figure 20-8, which gives us the locations of the centroids of all weld patterns. It has a distance C sub h from the edge of the column to the centroid of the weld, and a vertical distance from this point of maximum force, which could peel the weld off of the column. C sub v is the distance from that point to vertically to the center. We can calculate A as the distance from where the force is P to the centroid of the bracket, because we know E is 8 inches, B is 4 inches, and C sub h we know from figure 20-8. Here's some inputs to the problem. The total force is the weight of the motor. That's 3,500 pounds. E is 8 inches, B is 4 inches. The thickness of the plate T is a 1/2 inch. The Y height of the plate is denoted by letter D. That's 6 inches. X bar is the centroid distance from the edge of the pattern to the centroid, and that's equal to B squared divided by 2B plus D, which we're given. Hence we can calculate the value of A. And for the geometry factor for a bending, it's equal to BD plus a D squared divided by 6. In step 3, to compute the forces on the weld, we must know geometry factors AW and JW. We have twisting, hence we need to calculate JW, and we have a direct vertical downward force P, hence we need to calculate AW. And the location of the centroid of the weld pattern must also be computed. We're using case 5 in figure 20-8, which is the C shape for the weld pattern. Geometry factor A sub W is D plus 2B, which is equal to 14. Geometry factor for twisting is this complex formula here on the right between B and D. That comes out to 114.4 inches cubed. And the X distance from the weld centroid to the edge of the weld is denoted as X bar. It's equal to B squared divided by 2B plus D, and that comes out to 1.14 inches. The force due to vertical shear is 3,500 pounds, and when we divide by A sub W, which is 14, we get a vertical downward force per inch acting on all parts of the weld of 250 pounds per inch. To calculate the forces due to the twisting moment, we first have to calculate the torque due to the twisting moment T. And that's equal to P, which is the downward force, times the distance between that force and the centroid. E plus B minus X bar, and that moment is 38,000 pound-inches. Now the twisting moment causes a force to be exerted on the weld that is perpendicular to a radial line from the centroid of the weld pattern to the point of interest. So here's our force at the point of interest. It's angled down on this direction, and it's acting along this vector, which I show with a blue dotted line. And we have to break down that force into its horizontal and vertical components. And then we'll recombine those components plus that vertical force due to the shear force coming in from the load P. So we have to calculate some distances. C sub h is equal to b minus x bar. Here's b, that's the width, minus x bar, and that's 2.86 inches. The y distance from the weld centroid to the edge of the plate is c sub v, and that is equal to d, which is the total height of this leg of the weld, divided by 2, because there's our centroid. And the x force on the weld in the point of maximum force on the pattern is the torque T times CV divided by JW. And the y force of the weld is the torque times CH, the horizontal distance, divided by JW. Therefore, the total force at the point of maximum force, so that's this point right here, is 1199 pounds per inch, because it's the y force, which originally stemmed from the torque, so that's one y force, which is 949, F sub TV, 950 rounded off in our textbook, plus F sub S, which was calculated on the prior page of 250. I'm showing 1199 pounds. In our book it shows 1200. And the resultant force on the weld location, F sub R, is the square root of the horizontal force squared, which was the 997 number, plus the resultant y force squared, which was the 1199 number. And you take the square root of that. I got 1559. Our book called it 1560. And then the angle of this force is what I show here with the blue line as the actual vectoral angle. In step 5, we select the E60 electrode for the welding because this is a building type structure. It's definitely not a bridge. And the problem said we're using A36 type steel. We could have chose E70 if we wanted, but we chose E60 because the loads are, in the world of buildings, relatively small. We find that the allowable force per inch is 9,600 pounds per inch. We take our 1560 pounds per inch, which was small f, I called it 1559, and we divide by the 9,600 pounds per inch to get 0.163 inches. That's this step here in the spreadsheet. I called it 0.162. But it doesn't matter the small difference because we have to round up anyway to 0.188 inches because that's what table 20-4 is telling us to do for a plate that's half an inch thick. Let's study example 20-3. Determine the height of a welded strap for a load. A steel strap 1/4 inch thick is to be welded to a rigid frame to carry a dead load of 12,500 pounds, as shown in figure 20-10 below. Design the strap and its weld. The basic objective of this design is to specify a suitable material for the strap, the welding electrode, the size of the weld, and the dimensions W and H, as shown in this figure. The welds are only on the vertical sides of the strap. So the red line, there's 1, there's 2, and dimension T is into the page. Let's specify that the strap is to be made of ASTM A441 structural steel, and that it's to be welded with an E70 electrode using the minimum size weld 3/16 of an inch. Appendix 7 gives the yield strength of A441 steel as 42,000 psi. Using a design factor of 2, we can compute an allowable stress of 42,000 divided by design factor 2 equal to 21,000 psi. Here down on the bottom, I've dialed in all the input data to this problem. The required area of the strap A is the load P divided by the allowable stress, which is 12,500 pounds divided by 21,000 pounds per inch squared. And that equals 0.595 inches squared. But area A is on top of the strap, then the required width W is the area divided by T, which equals 2.38 inches. We then specify the round number of 2.5 inches for W. To compute the required length of the weld H, we need the allowable force on the 3/16 inch weld. Table 20-3 indicates the allowable force on the A441 steel welded with an E70 electrode to be 11,200 pounds per inch of leg size. Then small fa, which is the allowable force per inch, is 11,200 pounds per inch per 1 inch leg times a 0.188 inch leg, and that equals 2,100 pounds per inch. But Fa, the actual force on the weld, is the load P divided by A sub W, and that equals P divided by 2H. A sub W equals 2H because in this diagram, for A sub W, H corresponds to the length of these lines D, where A sub W equals 2D, sub in H for D, and A sub W is 2H. Solving this equation for H equals P over 2 times F sub A, and that equals 2.98 inches. And we specify H to be 3 inches as a round number. This is example 20-4. The goal is to design a welded joint for welding a tube to a plate. Here's our tube, there's the plate, and there's this odd-shaped plate here on the other end of the tube, which has a load P acting downward on it, offset from the x-axis. The tube is 14 inches long. We're going to weld a 1/4 inch fillet here, so that's this view, and a 3/16 fillet will weld this odd-shaped plate to the other end of the tube, and it's 1/2 inch thick plate. There's our load P, it's 2,500 pounds. This distance between the rigid surface and the plate is the 14 inches, and the distance from the x-axis to where force P acts is 8 inches. We will evaluate this design with regard to stress in the welds. All parts of the assembly are made of ASTM A36 structural steel. They're welded with a E60 electrode. The 2,500 pound load is a dead load. Because the static load P is offset from the x-axis, we're going to get bending, twisting, and vertical shear loads on this joint. And in particular, we're going to be interested in this point where my mouse is, because that will be the point of maximum force and maximum stress on this joint. At this point, we have a three-dimensional force system acting on the weld, as shown in this picture. We have F sub S in shear acting downward. We have the torsional force acting in this direction, and the bending force acting outward. The offset location of the load is what causes the twisting on the weld that produces the force. The bending F sub B acts outward along the x-axis, and that's from the fact that this tube is being pushed down, which creates a bending moment right here. And the vertical shear force is acting down because force P acts down. All of our critical information and dimensions that we had on the prior slide is shown here in this table at the bottom. Let's first calculate the twisting force F sub T. It's equal to the torque T times C, the distance from our point of interest to the neutral axis, divided by a J sub W, the geometry term. J sub W is simple here because we have a circular weld, and J sub W equals pi d cubed divided by 4, where d is the diameter of this circle, which is 4.5 inches. The torque T is equal to the 2,500 pound load times this 8-inch offset distance, that's 20,000 pounds per inch. And C is our outside diameter of 4.5, there's our diameter, 4.5 inch, divide by 2 is a 2.25 inches. J sub W is 71.57 inches cubed, and we calculate for F sub T and we get 629 pounds per inch. Now let's calculate the bending force F sub B. That force is the moment M divided by S sub W. S sub W for a circle is pi d squared over 4, where d again is 4.5 inches. And the moment M is a 2,500 pound force times the length of the tube, which is 14 inches. And that's 35,000 pound inches. S sub W comes out to 15.9 inches. The moment divided by SW is equal to the bending force on the weld, and that is 2,201 pounds per inch. Now let's calculate vertical force F sub S. F sub S is the load P, 2,500 pounds, divided by A sub W, where A sub W is pi times the outer diameter of 4.5 inches, which equals 14.14 inches. When we divide 2,500 pounds by 14.14 inches, we find that F sub S equals 177 pounds per inch. Now the resultant can be computed. Because our three forces, F sub T, F sub B, and F sub S, are all normal to each other, the resultant force is just the square root of F sub T squared plus F sub B squared plus F sub S squared, which comes out to 2,296 pounds per inch. Now we calculate W, the weld length, by taking the resultant force F sub R of 2,296 pounds per inch and dividing out by the allowable force on a 1-inch leg, which is 9,600 pounds per inch of leg size, and that is equal to 0.239 inches. Table 20-4 indicates that the minimum weld size is to be 1/4 inch, so we round up the 0.239 inches to 1/4 inch. Example 20-1 is for the design of a bolted joint for a frame. We did this problem in terms of a welded joint. This is the version of the problem for a bolted joint with 4 bolts. For the bracket of figure 20-4 shown here, assume that the total force is 3,500 pounds, and that force is acting at distance A equals 12 inches from the centroid of the 4 bolts. Design the bolted joint, including the location and number of bolts, the material, and the diameter. We've chosen 4 bolts. The center line between bolts 2 and 3 is 4 inches offset horizontally from the center line for bolts 1 and 4. The center line for bolts 1 and 2 is offset 3 inches vertically from the center line for bolts 3 and 4. In step 2, we determine the direct shear force on the bolt pattern and on each individual bolt, assuming that all bolts share the 3,500 pound load equally. We will also be selecting ASTM grade A325 for the bolts. In the table at the bottom of the slide, I have summarized all the input data for the problem. The shear load is 3,500 pounds in this 4 bolts. Assuming that the load is shared equally amongst the 4 bolts, each bolt has a shear load acting downward of 875 pounds. In step 3, we compute the moment to be resisted by the entire bolt pattern. The product of the overhanging load, 3,500, is multiplied by the distance to the centroid of the bolt pattern, which is 12 inches. The moment resisted by the bolt pattern is 42,000 pound-inches. In step 4, we compute the radial distance from the centroid of the bolt pattern to the center of each bolt. It's a symmetric problem, so each bolt has the same radial distance, and that's calculated by the square root of delta x squared to the centroid plus a delta y squared, which is square root of a 1.5 squared plus 2 squared, which is 2.5. In step 5, we compute the sum of the squares of all radial distances to all bolts. And in this problem, all 4 bolts have the same radius, so the sum squares of the radial distance is 4 times a 2.5 squared, which is 25 inches squared. The force that each bolt sees will then be the moment on the bolt pattern times r sub I, which is the distance from any bolt to the centroid divided by the sum squared. This calculates to 42,000 pound-inches times 2.5 inches divided by 25 inches squared, which is 4,200 pounds. Each of the 4 bolts sees this same bolt due to the moment. The force acts perpendicular to the radius. In step 7, we determine the resultant of all forces acting on each bolt. A vector summation can be performed either analytically or graphically, or each force can be resolved into horizontal and vertical components. The components can be summed, and then the resultant can be computed. The shear force acts downward in the y direction, and that's our 875 pounds F sub s on a bolt. The x component of this 4,200 pound force on the bolt is F1x times sine theta, where theta is a 36.9 degrees from the trigonometry of the bolt pattern, and that equals a 2520 pounds. F1y, here's F1y, is F1 cosine of theta, which is 4,200 times cosine of a 36.9 degrees, and that equals a 3360 pounds. We then add the 2 y forces algebraically, and we get that the y force is 4,235 pounds. And then we calculate the resultant force on the bolt as the square root of F1x squared plus Fy squared, where Fy is the total y force on a bolt of 4,235. And we get that the resultant force on a bolt is 4,928 pound force, and here is the direction that it is shown in. In step 8, we specify the bolt material, and we compute the required area for the bolt, and we select an appropriate size. We've already selected ASTM A325 steel for the bolt, which has an allowable shear stress of 17,500 psi from table 20-1. That's over here. My mouse is. Therefore, the required area for the bolt is 4,928 pounds is the resultant force, divided by 17,500 psi, which is 0.282 inches squared. And then we can find the diameter as the square root of 4as over pi. Because pi d squared over 4 is the area, we're just inverting that formula. And we find that the minimum diameter required is 0.599 inches. And we round up to the nearest larger standard bolt size, which is 0.625 or 5/8 inches. And here is the total solution to example 20-1, which gives all the calculations.